In this video, we're going to introduce the topic limits at infinity. So we're coming back to the topic of limits. We spent a whole chapter on it. We learned about some derivatives. Now we're coming back to it. There's two things we're going to introduce before we look at our first example. And the first is going to be the definition of a horizontal asymptote. So we're going to start off by saying the line y equals capital L is a horizontal asymptote of the graph of f when the following two conditions, or it just has to be one or the other, are met. So the first thing that can happen is the limit of f of x as x approaches negative infinity is equal to L. That's one case where y equals L is a horizontal asymptote. Or we can have the limit of f of x as x approaches infinity equal L. If either of those cases happen, then we've got a horizontal asymptote at y is equal to L. That's important because in the next lesson, so right now we're talking about limits at infinity. In the next lesson, we're going to discuss sketching curves. So everything we've done this chapter kind of is setting us up for sketching a curve. Now, there's also a theorem we're going to go over before we look at our first example. And that theorem is Theorem 310, which we call limits at infinity. We're going to start this off by saying if R is a positive rational number, and C is any real number, then the following can be true. If we have the limit as x goes to infinity of C over x to any power, that's going to equal 0. And the reason behind that is if we put infinity in for R, we're going to have something over an infinitely large amount, which means it's going to be such a small number, it's going to get closer and closer to 0. We say that the limit in this case would be 0. There is a little bit more I need to say about this theorem. So we're going to say furthermore, if x to the power of R is defined when x is greater than 0, then we say that the limit as x goes to negative infinity of C over x to the R is also 0. Now you can find a proof of this in our textbook. I'm not going to go over all that. I'm going to get straight into our first example. So, example 1, we are going to find the following limit. We're going to take the limit as x goes to infinity of 5 minus 2 over x squared. So if we think back to our chapter on limits, we can break this up. We can call it, make this the limit of 5 as x goes to infinity minus the limit of 2 over x squared as x goes to infinity. Now, from our limits chapter, we learned that this first part, the limit of 5 as x goes to infinity, that's equal to 5. And from the theorem we just wrote, this second part, the limit of 2 over x squared, that's going to be 0. So we're going to go 5 minus 0, which is equal to 5. So the limit of 5 minus 2 over x squared as x goes to infinity is going to be 5. So what that means is if we were trying to find a horizontal asymptote, we can say that asymptote would be y equals 5. So let's look at example 2 now. We are going to find the limit of 2x minus 1 over x plus 1 as x goes to infinity. So let's just take a quick note as to what is going on here. If we were to take the limit of the numerator and the denominator separately, so if we take the limit of 2x minus 1 as x goes to infinity, that's going to give us infinity minus 1, which is just infinity. And if we did the limit of x plus 1 as x goes to infinity, that's infinity plus 1, which is still infinity. So we'd have infinity over infinity. That's an indeterminate form. We can't do that. So to resolve this, what we do is we are going to divide by the highest power, the term with the highest power in the denominator. So in our denominator, in this case, the highest power term is just x. So we're going to divide everything by x. In fact, I'm going to write that up here. Divide, not even write, I'm going to type it for you so you can see it nice and written for you. Divide by the term with the highest power in the denominator. And that is just the variable portion of it. So, let's do that. We're going to divide this time by x. We're going to take the limit of 2x minus 1 over x plus 1 over x as x goes to infinity. Now if we actually simplify this, we're going to have the limit 2x over x is just 2 minus 1 over x over x is 1 plus 1 over x as x goes to infinity. Now we can start figuring this out. We can call this the limit of 2 minus the limit of 1 over x, and in both cases x is going to infinity, over the limit of 1 as x goes to infinity, plus the limit of 1 over x as x goes to infinity. From our previous chapter on limits, we know the limit of 2 is 2. We know the limit of 1 is 1. And from this chapter, this lesson even, Theorem 310, we know the limits of 1 over x are going to go to 0. So 2 minus 0 is 2. 1 plus 0 is 1. 2 divided by 1, our limit is going to be 2. If we tested this as x goes to negative infinity and got the same answer, that would mean y equals 2 is our horizontal asymptote. So now let's look at another example. Example 3, and I've got 3 different cases to look at here. 3a, we're going to find the limit of 2x plus 5 over 3x squared plus 1 as x goes to infinity. Now, the denominator's highest term with the highest power is x squared, so we're going to divide everything by x squared. So we're going to rewrite this as the limit of 2x plus 5 over x squared over 3x squared plus 1 over x squared as x goes to infinity. And then we can clean this up. 2x divided by x squared, we're going to get the limit of 2 over x. 5 over x squared is just going to give us 5 over x squared. Over 3x squared over x squared is 3 plus 1 over x squared. This is all as x goes to infinity. Now that I've been working with limits long enough, I'm not going to rewrite this again by separating everything. I know that the limit of 2 over x as x goes to infinity is 0. And I know the same thing is true if I have 5 over x squared. 0 plus 0 is in my numerator. I know that the limit of 3 is going to be 3, no matter what x approaches. And I know that the limit of 1 over x squared as x goes to infinity is going to give me 0. So I'm going to have 0 over 3, which is equal to 0. So the answer to this limit is 0. I have 2 more I want to look at. So this is still in example 3, but this one is 3b. We're going to look at the limit of 2x squared plus 5 over 3x squared plus 1 as x goes to infinity. So, again, the highest power in our denominator is x squared, so we're going to divide by x squared. So we're going to write this as the limit of 2x squared plus 5 over x squared over 3x squared plus 1 over x squared as x goes to infinity. And if you're confident in your work, you don't have to write the step I just wrote. But I should at least see this next step. So we can write this now as the limit of 2 plus 5 over x squared over 3 plus 1 over x squared as x goes to infinity. And again, I don't need to see you breaking this apart anymore because we know the limit of 2 is going to be 2. And our theorem, 310, says 5 over x squared is going to give us 0. We're going to get 3 plus 0 in our denominator, which is going to just result in 2/3. I've got one more, and then I'm going to give you some guidelines that kind of follow these 3 cases. So this is 3b, or 3c. We're going to find the limit of 2x cubed plus 5 over 3x squared plus 1 as x goes to infinity. The highest power in the denominator is x squared, so we're going to divide by x squared. So we're going to rewrite this as the limit of 2x cubed plus 5 over x squared over 3x squared plus 1 over x squared as x goes to infinity. Now let's simplify this up, clean it up a bit. We're going to have the limit of 2x plus 5 over x squared over 3 plus 1 over x squared as x goes to infinity. So we can now start plugging things in. 2 times infinity, that's going to be infinity, plus 5 over x squared as x goes to infinity is 0, over 3 plus 0, which gives us infinity over 3. And if we divide by this, we're going to just get infinity. Because of this, there is no limit. So this limit does not exist. If it goes to infinity, that means it's going to continually increase. There's no end. There's no spot where this can't cross. It just keeps going. So limit does not exist. Now for our guidelines. So here we go. Guidelines for finding limits. At both positive and negative infinity of rational functions. And rational functions, just as a reminder, look like those last few examples where it's got a polynomial divided by another polynomial. So the first thing we can say is if the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. Just like 3a. We had a higher power in the denominator. That's what we had to divide by. We ended up with 0. The second guideline, second thing to live by, if the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. Meaning, just take the leading coefficients and divide them. And lastly, if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. So you don't even have to always worry about evaluating the limit. If you can remember these 3 guidelines, you won't have to evaluate the limits anymore of rational functions. That's also going to wrap up this first video on infinite limits, or limits at infinity.